Now I will briefly explain the mathematical modeling of our final year project. First we move on towards the forward kinematics. Forward kinematics is a study in which we have to find the end effector coordinates when we know the angles, the offsets and the link lengths. And then we use the Dinavet and Hartenberg principle to find the values of d, alpha, a and theta. And then we use the transformation equation to find the transformation matrix. This is the transformation matrix from base to the end effector. And here you can see the x, y, z coordinates, but we have something unique observable over here. The x and y is independent of z and the z is independent of x and y. This is something very important in the dynamic torque analysis. Just remember it and I will discuss in the later slides. We move on towards the inverse kinematics. Inverse kinematics can be found out using the multiple ways. Well, basically it is a study in which we have to find the angles when we know the end effector coordinates, when we know the offsets and we know the link lengths. So basically we use a geometric solution over here. This is the top view of our Netrunner 4-axis robot. The only angles that contributes in the motion of the end effectors are theta 1 and theta 3. The prismatic joint is only making our robot go in the z direction. So the theta, to find the theta over here is of no importance because all of our revolute joints are revolving in the same axis. We use the law of cosines to find theta 1 and theta 3. We move on towards the static torque analysis. Now imagine if I suspend my hand in the air and there is obviously some force acting along each of my joints, each of my bones and everything. And my elbow and my shoulder will experience some sort of a torque. In order to float my arm in space, I need to provide some reverse torque. This is the same principle in the robotics. We have to find that reverse torque to keep our robotic manipulator static in free space. So this is the equation that we found out. And then now we've moved towards the dynamic torque analysis. If before I move any further, I want to introduce you to the abbreviation that I'm going to be using in my presentation. The link lengths are represented by A and all the offsets are represented by D, and the masses of course M1, M2, M3 and M4 is the mass of end effector. This is our dynamic torque equation. I have divided it into two categories. As you can see, and as I discussed in the first slide, that those xy are not dependent on z and z is not dependent on xy. So the prismatic force, that is F2, is independent of any torques, and it's actually dependent on the torques, but the thing is the M2 I use is from the MATLAB simulation. It contains all the masses acting throughout the robotic manipulator, and it's like 7.2 kg is of the whole arm extended. And it can be simulated in MATLAB or in a 3D environment, a virtual environment only. So these are the torques T1 and T3 that are of the base revolute joint and of the elbow revolute joint. There are three elements can be seen over here. The theta, the first term is of theta 1 and theta 3 double dot. It's like it's the element of the angular velocity of joint 1 and joint 3. And if we move on towards the next one, we have the kinetic energy element of joint 1 and joint 3, and same is with the case. And there is something very important over here. The third element is of the most importance. Theta 1 dot, like angular velocity of the first joint multiplied by the angular velocity of the third joint. It means that if I want to move my arm in the space, I will obviously have some different angular velocity of my shoulder joint and some other angular velocity of my elbow joint. So these shows the dependency of angles on each other in order to achieve a certain point in free space. This dynamic torque analysis can be solved in MATLAB using J trajectory. So that's pretty much it. I would like to call Jahangir to discuss his computer vision presentation. Thank you.